Bismillahirrahmanirrahim. We are going to continue with making the Excel sheet for the axial compressor design that we have just finished. So we did the design for the first stage and then we proceeded with the design of the second stage and the design for the stages 3, 4 and 5 will follow a pattern similar to that for design of stage 2. So therefore instead of doing everything on paper, we are going to now open an Excel sheet and do the rest of the design of the remaining stages using an Excel sheet. So let's get started with filling our Excel sheet. So on the screen we have our Excel sheet on one side, on the right hand side, and on the left hand side is our table of equations. So as we have done in the other designs, we are going to follow the same sequence of equations. So the very first thing we will do is we will calculate the number of stages. Now before that, so that is the very first design step, but before that let's write our design specifications. So our design specifications are the pressure ratio. Our pressure ratio is 5, the mass flow rate, which is 30 kg per second. Please go back to your notes. We also need the stagnation temperature at the inlet, which is 300 Kelvin or 27 degrees centigrade, and then our stagnation pressure at the inlet 101 kilopascal. And if we need some other variables or constants, we can define them over here. So now we could do some formatting. Let's give names to these variables. So that is your pressure ratio, mass flow rate M, T01. Let's see if that works. There is a problem. So T0_1, that works, and P0_1. Okay, so we can get started with our preliminary design, the very first step. Now also we need to start with a certain RPM. So the RPM we have picked in the beginning 15,000. Okay, so let's give it a name as well, N. Okay, and we can convert it to omega because that is needed at certain places in the calculation, to a pi n divided by 60. So that's your omega. Let's give it a name, omega. Okay, so now we can start with our preliminary design, which is the number of stages. We have to calculate the number of stages. Now in order to do that, we need to find out. So the equation is number of stages equal to delta T OE, which is the total change in temperature or stagnation temperature across the entire compressor, divided by the change in temperature across one stage. So therefore we will need to calculate the delta T OE first, and then we will calculate delta TOS, and once that is done, then the number of stages can easily be calculated. Okay, so we have our formula over here, this particular formula over here, P0E by P0I equal to 1 plus adiabatic efficiency delta TOE by T0I K by K minus 1. So we know P0E by P0I, which is the pressure ratio. We can fix an adiabatic efficiency. T0I is known, and therefore from that formula we can find out the delta TOE. Okay, so let's do that. And now we need to fix an adiabatic efficiency. Let's take it as 0.9. Okay, and give it a name to access it later, an adiabatic efficiency. Okay, alright, so the formula is, let's feed the formula over here. So it's T0I, which is actually T01, divided by the adiabatic efficiency into RP to the power K minus 1 divided by K minus 1, and that's it. Okay, so when we enter that formula, it's going to give us an error because we do not know the value of K. So K is 1.4. that is the K value for air. Okay, so once we feed that value, we can get a number over here, 194.6, which is what we have gotten in our in our manual calculations also. Now delta TOS, how do we find delta TOS? Delta TOS, a range is recommended. So delta TOS should be taken between 20 to 60 degrees. Okay, so we have chosen 40 degrees. So therefore the number of stages is simply dt is equal to dTOE divided by dTOS. And again we have not given names, so let's go ahead and name them, dTOE and dTOS. Okay, and then we are going to say round up this formula, comma 0. So it is going to round it up to the next highest integer value, defined name. Okay, number of stages, fine. Alright, so we are done with calculating the number of stages. Now for the first stage we want to calculate the R tip, the R hub, and then find out the R mean, and after that we need to find out the blade angles, beta 1 and beta 2. Okay, so if you go back to your notes, we need to start with that particular equation over here, rho VA pi R tip square 1 minus nu square. So we need to find out the value of rho, and rho is given by, so rho 1 equal to P1 by RT1, and P1 and T1, both of them are unknown. So let's go ahead and input the value for R for air, which is 0.287. Okay, and define a name. Okay, so now if you follow the sequence that we adopted for calculations, in order to find out the P1, we need that formula. So P1 by P01 equal to T1 by T01 K by K minus 1. We know P01 and T01, but we do not know T1, and T1 is equal to, so from that formula T1 is equal to T01 minus V1 square by 2 Cp. So therefore we will have to assume the very first thing we need to do is we need to fix a V1. So our V1 or we can fix V axial. So V axial, we will fix it, we have fixed it as 550 feet per second, and we can convert it into meter per second. So let's give it a name, VA FPS, feet per second. Okay, FPS, feet per second, and let's convert it into VA FPS. Feet is 12 inches into 2.54 centimeters divided by 100. So that is your value of VA. Let's give it a name. So VA. Okay. So now our V1 is equal to VA, and from our VA we can calculate our T1, which is equal to T0 underscore 1 minus V1 square divided by 2 times Cp, and the Cp value is not known, so we can enter it over here, 1004. That's your Cp value. Give it a name, define name Cp. Once you do that, T1 is equal to 300 did we define that name? We did not define that name. Define name, so V1 MPS, meters per second, V1 MPS. So let's go ahead and change that formula, V1 meter per second, and enter. So 286 Kelvin. Now please note that we have a mistake in our manual calculation in this particular step. So instead of writing divided by 2 Cp, we in the manual calculation that 2 was omitted. So there is a difference between the manual calculation and the calculation that we are doing now. Okay, so now P1 is equal, we will get our P1 from that formula. So P1 is equal to P01, and it's not picking up P01, P0 underscore 1 multiplied by T1, is it? No, T underscore 1. Actually we have not defined that name. So let's go ahead and define the name first. So define name T underscore 1. So this is equal to P0 t0_1 multiplied by t1 divided by t0_1, and that t0_1 is also not defined. Anyway, we can define it to the power k minus 1 divided by k, and enter. This is your t01, t0_1. Okay. We are having trouble with our, so that one is also not defined. t0_1. Okay. Oh, we have a problem. In adiabatic, we have a issue with the naming, unfortunately. So we will have to think of something. Define name. Is it going to take p01? Just to make it simple, I'm going to call it p01 or p0 inlet, in p0 in. p0 in. Okay, so now we have a value p1 99.63 kilopascal, and now we can go back to our formula for density. So rho 1 it is equal to p1 p I don't think we have defined that name. We are having problems with defining our names. p_1. Okay, so rho is equal to p_1 divided by RA into t_1 T1. So that gives us our rho 1, and it is equal to 1.213776 kg per meter cube, and that value is also different from the value we have obtained in our manual calculations. So let's put a name, rho 1, and now we can calculate our R tip. So the R tip is equal to square root of mass flow rate divided by density rho 1 into V axial into pi into 1 minus nu square. Okay, and it is going to give us an error because we have not defined our new or the hub ratio. So let's take our hub ratio as 0.5 and give it a name, new. Once you do that, you have your R tip. So 0.250148 or approximately 25 centimeters. So your R hub will be, so let's give this a name, R tip. Okay, R hub will be equal to mu times R tip, and that is your value, and R mean is equal to, so let's give this one a name, R hub. So R mean is equal to R tip plus R hub divided by 2. Okay, and we can continue in the same line and get our beta 1 and beta 2, or if you feel don't feel comfortable, you can go to a separate line. So that is your R mean, and let's get started with calculating our beta 1 and our beta 2. So let's do it on a separate line, since it is becoming too long. So tan beta 1 is u1 by v1. So we need to find out our u1. So let's calculate u1. So u1 is equal to, or actually just to save space since we are doing it, let's calculate our u1 over here. It is equal to omega into R mean. Well, once again we have not defined our R mean, so here is our R mean. Once you define that, you will get a value. Okay, so 294.69 approximately meter per second. So our beta 1 it is equal to A tan u1 divided by v1, and we have not okay, v1 underscore meter per second, and u1 has not been defined, so let's define u1 meter per second. So u1 mps, and we can convert it into degrees. So let's give it a name, define name, beta 1 underscore radians. This is in radians, and then we can convert it into degrees. So 60.36651 degrees, and now we can calculate our beta 2. Let's do it in the same line, although as I said, if you wish to go to a separate line, you can do that. Actually, I don't know, it may even be a better idea to do it in a separate line. But this is totally up to you how you program it. Okay, so let's go to our formula for tan beta 2, which comes from here. So Cp delta TOS equal to lambda UVA tan beta 1 minus tan of beta 2. So we rearrange the terms and we can get our beta 2. So let's write our beta 2 over here. Or before we go to beta 2, we can declare our lambda, which is 0.98. so here is your lambda. Define name lambda, because we will need the lambda value. So beta 2, it is equal to a tan, and then tan of beta 1 in radians minus Cp into dTOS divided by, so let's put a bracket over here to be on the safe side, divided by lambda into u1. Where is our u1? Let's check. u1 meter per second into VA. And that is your beta 2. Let's define it, beta 2 underscore radians, and then we can convert it into degrees, into 180 divided by pi. So 42.8746 degrees. So those are our design values: R hub, R tip, R hub, R mean, U1, so beta 1 and beta 2. So that completes our design for, actually no, we need to do the check. We need check. So check 1 and then check 2. Or actually, in order to do the check 1, we need the value for R. So R is equal to, VA into tan of beta 1 radians plus tan of beta 2 in radians divided by 2 times u1 and in meter per second. So that is your R value. So it turns out to be 0.76, and I hope that we are doing things correctly. So let's define the name R for stage 1. So let's call it R1. Okay. So check 1 is the new min. So new min is equal to 1 minus R underscore 1 to the power 0.5. So that is your new min for stage 1. So new min is new is bigger than new min. So our condition is met, our check is okay, and then we need to do check 2, which is W2 by W1. So that is equal to cos of beta 1 in radians divided by cos of beta 2 in radians, and that value is actually not checking out properly, so we will put a red mark over here. So that value is incorrect. It needs to be in the range 0.7, between 0.7 and 1, and it is just slightly below 0.7, and you are going to adjust some values, maybe this parameter over here, and see if you can get this check to be correct. So we will stop at this point of time. We are done with the design of stage 1. Stage 1 design is done, and in the next lecture coming up very shortly, we are going to start with our design of stage 2. We cannot do it in one lecture. The lectures become too big, and it is difficult to save them as a video file and also to upload them. So we will continue in part 2 of this lecture. Thank you very much.